Okay, so last class we have actually so far discussed about a few fundamental maybe definitions and concepts in probability, and now we will see maybe a pattern recognition problem. Okay, maybe which is actually based on this probability. Okay, so how we can actually use the probability maybe principles for a pattern recognition problem. So, for example, maybe classifying fish in our example into a sea bass, okay, or a salmon, okay, or maybe any classification problem or any pattern recognition problem, maybe we are actually interested in. So here, uh, this is actually based on the particular pattern recognition is actually based on the Bayesian decision theory. Okay, I think we have already seen the Bayesian decision say theory. Okay, so we'll come to that maybe results and maybe equations. In the coming slides. But before going to the details of maybe how that the Bayesian decision theory is actually used to maybe make a decision on for classification. So it is actually based on two assumptions. So that this is actually built. One is actually the decision problem is actually posed in probabilistic terms. So that is one assumption. Then only we can actually apply Bayesian decision theory. And another one is actually all the relevant probability values are actually known. Okay, so the required probabilities that we will see, which are the required probabilities, they are known, and before that, the problem is actually represented maybe in terms of probability. So these are the two assumptions that we make in order to apply the say the Bayesian decision theory. So that means maybe in our example, okay, maybe we are assuming that the fish that is arriving is actually in a random. So because that is okay, we can assume that the fish coming in the conveyor belt is actually a random fashion. Then assume that we just mentioned that so whether it is a particular fish or another fish, we assume that the state of the nature. Okay, so we assume that W represents a state of the nature. So that means which state, in which state the nature is. So that is whether it is in sea bass or salmon. In one case, maybe in class A or class B, or in class C, maybe in another case. Okay, so we assume that the state of the nature is W1, okay, when sea bass comes, and maybe say W is equal to W2 when say salmon, okay, arrives. So that is actually the concept of state of the nature. And so we assume that the state of the nature is actually unpredictable. Okay, so we maybe formulate this as a random variable. Okay, so then we see that W to be described probabilistically. Okay, so that is as it is unpredictable, we can use maybe they can be maybe described in terms of probabilistically. So that means suppose if the catch, that is catching the fish, okay, produced as much as sea bass, okay, as salmon, okay, then we can say that the chance of occurring, okay, W1 or W2 is actually equally likely. So that is we can say, okay, equally likely probability that the next one, okay, the next fish arrive is actually salmon, and or the next fish is actually sea bass. So that depends on how the probability, okay, of individual, okay, maybe state of nature is actually maybe say vary. So that is actually one point. Okay, so then we'll move to the next one. Okay, then let us assume that there is some probability. Okay, there is some probability. Okay, called a priori probability or a prior probability. Okay, so that means that is what we have just seen. So the probability that the next fish is actually sea bass. So here, assume that you are actually you don't know anything about the features. Okay, suppose there is a situation. Okay, there is no. So, and you are actually told that okay, the probability that the next fish is actually sea bass is this one, and the probability that the next fish is salmon is this particular value. So that is a you are actually not seeing any fish. Okay, but you are given with some probability value. Okay, the what is the probability for a next fish is sea bass or next fish is a salmon? So that probability is actually called a priori probability, or generally called as a prior probability. Okay, so let us say P of W1, okay, for maybe say sea bass, okay, and P of W2, okay, for say salmon. So these are the two probabilities that we will maybe make use of. So that is a prior concept of prior probability. And as we have only two fishes, okay, that means only two classes. We have a P of W1 plus P of W is equal to 1. Okay, because they should actually maybe the entirety is actually maintained. So that is actually our the idea of prior probability. Okay, so that means it actually reflects okay our prior knowledge of how likely we are to get a sea bass or a salmon. Okay, before the fish actually arrives. That is an important point. So that means our aim is actually we will have a fish arriving on the conveyor belt, and then we have to predict or say classify. That is our ultimate goal. But before the fish arrives, what is with you? Okay, what knowledge is with you? That is one such information that is with you is actually the prior probability. Okay, so then the prior probability how it can maybe vary in this particular case. Okay, so that is maybe for example area of catching can give you a probability value. Okay, and time of year. Okay, so all these are some of the okay say situations or maybe the context that will give you maybe different values of prior probability for maybe P of W1 and P of W2. You can find other context or maybe environmental factors or any other okay maybe who is actually maybe finding out this prior probability that can also have a lot of impact. Okay, so whether a very relatively new okay fisherman or maybe a very inexperienced fisherman who is actually maybe fishing at a particular place for say 20 plus years or 30 plus years. So there are a lot of things that can actually maybe depend on also can influence the prior probability. But assume that we depending upon the problem we will have again that depends on, so for example if it's a medical condition, then you take a very experienced doctor or you take a maybe a relatively say a very new okay doctor to the service. So in such cases also there's a chance that the prior probability can vary. Okay, whatever what condition or say situation you are actually taking in order to define the prior probabilities like based on that. So that is a concept of prior probability. Okay, then okay, then suppose without observing any fish at all. Okay, suppose you are actually told to make a decision. Okay, that is what is your decision, or maybe you have to make a model. Okay, that is what is next fish arrives. Okay, so suppose if that is a situation there. Okay, so that means without allowed to see any fish that is arrives, then we can make use of this prior probability. Okay, and we can actually maybe arrive at decision rule. So that is a concept of decision rule actually. Okay, so the decision rule is nothing but which rule we are actually using in order to reach a conclusion that the fish next arriving is actually this one or that one. Okay, so if that is the case, then what we can, the decision rule that we can formulate is, for example, we decide, okay, we decide W1 if probability of W1, that is prior probability of W1 is greater than prior probability of W2. So for example, the 70 percentage, okay, is a probability that, okay, the particular, okay, P of W1, then we can always predict that, okay, but the next fish arrives is actually say W1. That means say for example sea bass or salmon, whatever. Okay. Similarly, if W2 is larger, okay, then we will change the rule. That is, if P of W2 okay is greater than P of W1, then our decision will be W2. Okay, that is going to be the prediction by the model. So that is a simplest maybe decision rule that we can actually formulate using a probability. Okay, so that means here we are assuming that a prior probabilities are given, otherwise you will not be able to formulate such a decision rule. Okay, so that is a case. Okay, so then, so here, very interesting thing is, suppose, so for example, you are asked, you are given these values, and you are actually asked to find out, predict it. So, if it is a one fish or two fish, then most probably you will be having your prediction will be correct. Suppose repeatedly, maybe for example, 100 times, okay, 100 fishes are coming, and you are making use of the same rule, okay, in order to make a prediction, we can say that it is going to be a wrong prediction at many times. Okay, that depends on if it is 70-30, then 70 percentage you will be 70 times you will be correct, and maybe 30 percentage you will be wrong. Okay, so in that case, it is not the best rule actually. Okay, so that means if you are repeatedly are applying it, then we can look strange. Okay, because we know that both types of fish will appear, so it's a very not the best efficient way of maybe deciding. So that is a one issue with the prior probability alone. Then, so for example, that depends on, okay, so for example, if the probability of W1 is very large, then probability of W2, for example, 95 5 percentage. Okay, 95 is 0.95 is probability of W1, and say 5 is actually, say sorry, point not 5 is actually the other one, then there is no issue, because your probability is actually maybe the prediction will be more or less say same. But there can be situations that the probability of W1 is equal to probability of W2. That is 50 percentage, maybe the probability. Then, if you are using the same rule, then we can say that the 50 percentage will be right, and 50 percentage we are going to be wrong. So that is a very bad maybe scenario. So that is maybe the case with a decision, okay, based on prior probability alone. Okay, suppose we bring in some additional, okay, additional probabilities also, additional information also, maybe after observing the fish. Okay, so that means after observing the fish means you have maybe a set of features available, okay, for the fish, or maybe whatever maybe sample that you are actually observing. Okay, so if we can have additional information based on maybe this particular say features, then that will be maybe overcoming this drawback of maybe using single probability. Okay, so that is maybe what we are going to, okay, maybe based in decision theory, okay, maybe using additional probability values, so that we will see. Okay, so here, assume that our x is, okay, maybe a continuous random variable. Okay, we are making use of continuous random variable, and we assume that x is actually a feature. So it can be a feature vector itself. Okay, maybe we are considering multiple features. Otherwise, for example, if lightness of the fish alone, or width of the say, or say maybe length of the fish. Okay, it's a single feature you are considering. It's a feature. Okay, then. Then now comes, maybe we have an additional probability, okay, maybe along with the prior probability. So that is actually called a class conditional, okay, probability density function. So it's an additional probability that we will get, okay, after observing maybe the fish that arrive in the on the conveyor belt. Okay, so that is a case. Okay, so here it's a condition probability. Okay, so that means here the state of the nature is actually given. Okay, so that means you are observing that the next fish coming is actually maybe say sea bass. Okay, so that means you are given W, and then you are actually looking for what is the probability that the given X. So that means the X can be, suppose if it is a lightest value alone, then you will have a one feature. Okay, otherwise you can have maybe, okay, maybe if it is x alone, otherwise you can have x1 x2 etc, say xd. Okay, that can be a feature vector itself. Okay, so that depends on. Anyway, so here you're assuming that the state of the nature is known, and then what is the probability? So that is actually called a class conditional probability density function. Okay. So that can actually maybe based on maybe if there are two states, then let us say probability of x given w1, and for the next one probability of x given w2. Okay, so that they are the two class condition probabilities. Okay. uh, so that means here the difference in feature value of two types of fishes are actually considered. Okay, and these two probability differences will be is based on the features, okay, of the two fishes. Okay, then assume that we measure the feature. Okay, we measure the feature and observe that its value is x. So that means once you are actually given x, okay, the feature vector, okay, or a simple feature, we know that this is a lightness value. Okay, so or say length of the fish, whatever it is, or maybe a combination of maybe say two feature or three feature. So that means we know that particular value, and we know the prior probability also. Okay, and now assume that we have maybe found out this class condition probability also. Okay, based on the state of the nature that we have actually, because you have you have a probability of x already known. Okay, because you are actually measuring the x value, and then you are assuming that that particular value, that probability is actually known, and then we know what is probability of x given, okay, w2 or w1, that is known. Okay, so if we know all these probability values, okay, then we can write the Bayesian decision rule as we have discussed okay, the equation earlier. So that is what we are looking is probability of, okay, you are given x, so that means if either a feature or a feature vector is given, then we have to find out what is wj. So that means whether it is w1 or w2 or w3. Okay, but we have to find out the probability for each of them, that is actually equal to, according to the Bayesian say probability, it is probability of x given wj. Okay, so this is a class conditional probability we have seen, and this is probability of j, so that means it's a prior probability, and it is probability of x. Okay, so probability of x is actually that evidence. Okay, so that means what is the probability that a particular feature vector will exist. Okay, so that is a case, and that can be, okay, because while we discussed the Bayesian maybe probability, okay, we have seen that you can obtain probability of x for, okay, summing it over, okay, this one is, okay, throughout okay, all the classes. So that is actually the idea behind the Bayesian rule. Now we will discuss this in detail. Okay, but before that, let us. So then, the idea behind the Bayesian decision rule is that so we will be actually keeping that for which x given wj is, sorry. Before that, we have one more, fourth one is there. Okay, yeah. Okay, so this was a thing that we have discussed. Okay, so we have seen this Bayesian decision rule, and this is actually maybe represented in, or maybe say, written in this particular form. So we know that the probability of, okay, wj is actually called a prior probability. Okay, and so this step, that is a class conditional, okay, probability density is actually called a likelihood. Okay, and evidence, that is p of x. Okay, because evidence is actually after maybe you are given that particular feature vector, so that is, it's an evidence. Okay, you have actually maybe measured, okay, the what are the say x vector. Okay, so that's why it is called an evidence. Okay, then prior probability is already known, and then we have this class conditional, okay, density function. Okay, that we call it as a likelihood. We will see why it is called a likelihood shortly. So on the right hand side, we have a likelihood into, okay, that is probability of x given wj into probability of Wj divided by probability of X. So all these actually maybe contribute to a probability called a posterior probability. Okay, so the posterior probability is actually the Bayesian probability, and resulting in maybe based on the terms on the right hand side of the equation. Okay, so that is a posterior probability is equal to likelihood into prior probability divided by evidence. So that is a Bayes decision rule, and now we will be looking at which maybe posterior probability is actually larger, or the largest one, considering the different classes like W1, W2, okay, or maybe generally Wj. And based on that, we will be taking a decision on maybe to which Wj we have to assign the maybe or maybe which Wj we have to assign for the given say feature vector X, or for the evidence X. Okay, then so say here why it is called a likelihood. Okay, because we have seen a case where prior probability alone. Okay, so prior probability alone, we know that that is not going to be the best maybe decision that we can make it. So what we have done is we have actually then maybe looked at the evidence for a given feature vector X, and based on that, okay, suppose that a prior probability is given, okay, or maybe the same. Okay, for example, probability of W1 is equal to probability of W2. Suppose in our case, assume that we have a case of observing C bars and observing maybe say Sandman are actually equal. Okay, so that means 50-50 percentage. And then we know that probability of X is going to be same for whether it is W1 or W2, because probability of X is a term which is independent of W1 or W2, because this is about a fish is arriving and we have just measured its feature vector. Okay, before deciding whether that belongs to sea bass or salmon. So that means P of X is also is going to be same for maybe our decision say rule. So that means suppose we are actually measuring likelihood of Wj, okay, with respect to X. Suppose other things are being equal, then the category Wj, uh, so the category Wj for which probability of X given Wj is larger is actually more likely to be the true category. So for example, if prior probability and evidence are same, okay, or say maybe because they are going to be same, maybe in a particular say decision making, if that is the case, but there can be a situation where prior probabilities can be different, but evidence is going to be a just a normalization factor or a scaling factor, because that is going to be common for whether it is W1 or W2. Okay, because that is a measured thing, and measured thing based on measured feature vector, we are going to predict, okay, or make a decision that whether the class belongs to X1 or X2. Okay, so we can say that the evidence part is actually a normalization factor, scaling factor, that is we maybe ignore. Okay, and if P of W1 is P of W2, okay, then we can say that for which the class condition probability is larger, okay, they are going to be likely the class or the true category that we will be predicting. So that is why it is called a likelihood, okay, function. So that is actually the idea, the basic understanding of maybe a Bayesian decision rule. Okay, so now what we will do is we'll go to, okay, we'll go to another presentation. Okay, the initial slides are going to be almost the same. So that means if you look into the Bayesian decision theory, okay. So what we are actually looking is we are to design the classifiers to make recommendations. That means the decisions that will minimize some total expected risk. Okay, so that is actually what the maybe the Bayesian decision theory is all about. Okay, so now the simplest risk. Okay, the simplest risk means okay, the risk in the sense that okay, what is going to be the cost or risk involved in classifying a given fish. Okay, as a maybe salmon or as a maybe say sea bass. So there can be different circumstances. One is actually the simplest risk is a classification error. Okay, and assume that the cost involved in the classification are actually equal. So, for example, I have mentioned a particular case where okay, just a, just a moment. Oh, okay. So I have already mentioned that there can be a situation that say this classifying maybe say salmons, okay, as maybe sea bass, okay, similarly classifying sea bass as salmons. So that can have a maybe a different impact on the maybe companies, maybe reputation, as well as maybe income, etc. Okay, so that means the cost involved can vary. So the cost involved can vary with respect to a decision that we make. But for assume that okay, the wrongly predicting sea bass and wrongly predicting salmons for the time being, if they are actually say equal, then the risk okay is actually the classification error. Okay, so that is a important thing. Okay, then but if the costs are actually not equal, then we can say that the risk includes the costs associated with the different decisions also. Okay, so you can actually always bring in additional factors also into the maybe the risk. So we will see that one. So anyway, that is another important thing that we have to keep in mind. Um, Okay, this is the terminology that we have already seen. So that is a state of the nature. It's a random variable probabilities. Okay, I will quickly go through prior probability and the probability density function. Okay, evidence. All this we have just see. Okay, so that means now this is maybe the class condition probability. Okay, that is a likelihood that we have already seen. Okay, then assume that this plot okay is nothing but assume that we consider as a feature likeness. Okay, so that is probability of x. Okay, maybe given wj, that means probability of lightness given w1 and w2. Okay, so that is a probability of x given w1 and probability of x given w2. Okay, so these are the two but the probability of, this is for x1. Okay, and this is for maybe say the other case. Okay, so the class conditional probability distribution okay can be plotted, and based on that maybe okay you will get we can have a lot of maybe interesting okay points that we can actually maybe understand. So anyway, this is a plot. So we will come to this particular plot again. Okay. So similarly, you can maybe look for what is the prior probability value, and accordingly we can plot maybe what is going to be probability of W1 given X. Okay, and probability of W2 given X. So because these are the probabilities that we are trying to find out in order to make a prediction. So here the point is that you are given the feature vector x. What is the probability that it belongs to x belongs to w1, and here you know x. What is the probability that it belongs to the class or category w2? So that is actually the idea, and okay. So this is a posterior probability. Okay, I think that we have just described actually. And this is a decision rule okay with the prior probabilities alone. I think we have seen. And one more point is probability of error. Okay, it's nothing but a related concept. Suppose we have a we suppose we probability of w1 okay say we wrongly predict it okay using the prior probabilities alone. Okay, then suppose that we decide w2 okay but originally the class one is actually w1. So in that case the probability of w1 okay is going to be the probability of error. Similarly, assume that we decide okay when we decide w1, then what is the probability for w2? That is going to be the probability of error in that circumstances. So so that is maybe how we can actually define probability of error. So that is a another important point, but which is actually maybe closely related to the decision that we actually make it. Okay, so if we have correctly predicted it, then we can say that the error is actually minimized, or okay. So that means we can say that the probability of error is actually minimum probability of W1 and W2. Okay, because the larger value we will be making use for prediction, because that is actually the decision rule is about. Okay, because if probability W1 is larger, then we decide as W1. Otherwise, we decide as W2. So then, which is the minimum probability, that is going to be the probability of error. So that is a concept of probability of error. Okay, maybe this is using the prior probabilities around. Okay, so the same. So that is a case, and this is the Bayes rule. Okay, just we have seen. Okay, okay, nothing additional here. Okay, and we can say that this is a, decision rule here. That is, we can say probability of W1 given X and probability of W2 given X. So we will calculate the two posterior probabilities. Okay, and based on which is larger, we will assign the class level. That is either W1 or we decided W2. Okay, so maybe this is actually using the LHS of the maybe the base rule, but we can use maybe the RHS side of the rule also. Okay, and we are assuming that the evidence is going to be common. Okay, because we know that the probability of X is common for whether it is W1 or W2. Okay, while making a decision. Okay, so that means in that case the class condition probability into prior probability of W1 greater than corresponding for maybe say W2, then we will make a W1, otherwise we will make a okay, W2. So this is the rule is actually same, only thing one is actually based on the LHS posterior probability value. The right one is also maybe in terms of the likelihood. Okay, this is the likelihood, and this is a prior. Okay, so that is a decision rule that we can actually make it. Okay, and now this is actually maybe earlier we have seen a plot of probability of X given Wj. That is a class conditional plot we have already seen. Okay, and assume that we have a okay, this is the probability of the prior probability. So that is probability of W1 is equal to 2 by 3 and probability of W2 is equal to 1 by 3. Let us assume. Okay, then suppose we plot the posterior probability, that is probability of Wj given X. Then assume that we will get a maybe a plot like this one. Okay, for different for different X values. Okay, then you can see that okay, at various places. Okay, the probability of W1 is actually larger than probability of W2. In some cases maybe the probability of maybe W2 is actually larger than maybe okay, that of W1. So correspondingly, whenever the say a fish actually takes a corresponding X values, we will have a this value okay, larger for in some cases for W1 and in other cases for W2. Okay, but one thing is suppose we take a particular maybe say suppose we take a particular value here. Okay, say for example, okay, suppose if this, then we can see that at this point, okay, and maybe this point, that is probability of W2 given X and the probability of W1 given X. So in that case, we can say that if they are added together, okay, if they are added together, then that should be equal to 1. Okay, because that is a complete, okay, the what that only we have only two classes. Okay, and they should actually add it to okay, one. So that is actually the posterior probabilities okay, should be added to one also. So that is a interpretation okay, that we can actually maybe okay, do here. Okay, so that is a case. Then we can actually maybe extend the concept of probability of error to Bayesian case also. Okay, the same as the that with respect to prior probabilities alone. So that means here the only thing is assume that we have probability of error given X earlier. Okay, we have not considered that the X factor. But here also we are assuming that the probability W1 given X, if we decide as W2, the rule remains same. Only thing we are assuming that the x is given. Okay, that is we have observed one feature vector. Okay, and similarly here also, and this also remains the same. That is probability of error given x is again minimum of, okay, this one. Okay, because maximum is we have already used for the prediction or the corresponding class. Okay, so that is actually again probability of error with respect to Bayesian, and then we can maybe define the average probability of error also. Okay, so that means we assume that uh, probability of error, okay, maybe it's an average case. Okay, we know that these are going to be the density functions, so we integrate, okay, or from minus infinity to infinity probability of, okay, error comma x, okay, into dx. And we have already seen this particular, okay, substitution we can make, okay, based on our earlier discussions. So it is minus infinity to infinity, okay, the joint distribution, okay, we can actually represent like this one, that is probability of error given x into px into dx. Okay, so here we can say that suppose we try to minimize this particular quantity. Okay, we try to minimize this particular quantity. Okay, that is probability of error given x. That means for each x, suppose we try to minimize probability of error given x, then we can say that the whole quantity will be minimized. Okay, so if we are for each x, because we are considering all the possible x feature vector here. So in that scenario, if we are trying to minimize, okay, the probability of error given x, okay, for each x, then we can say that the whole integration will also result in the minimum value. That means we are actually, we can say that the base rule is actually optimum. Okay, that means it is minimizes the average probability error. Okay, in all the in all cases, it actually tries to minimize the average probability of error. Okay, so again, that's why base rule is actually called an optimum one, because you try to minimize the individual probability so that the average probability is also in effect maybe say reduced. So that is actually maybe the concept of probability of error, and why we say that Bayes rule is an optimum one. Okay, maybe considering this particular case. Okay, so I think with that we will stop today. Okay, and maybe we'll continue from next class onwards. Okay, so thank you for listening.